It's not long ago that Joe Biden won the presidential election in the United States. It could have gone the other way. Donald Trump could have won, and if that had happened, things would be quite different now. We could imagine an even more radical outcome. One way or another, somehow Kim Kardashian could have become President of the United States and appointed members of her family to all senior government positions. An all-Kardashian United States government would have a significant impact on the world compared with the way we see things now, especially regarding such topics as plastic surgery and makeup. And yet in all of these different worlds, some things would remain true. For example, 2 plus 2 would always equal 4. P or not P would always be a tautology. So we can see that somehow there are certain truths which are, we could say, contingent on the particular world that we inhabit, and other truths that are somehow immutable. Modal logic tries to capture this concept through, well, here we get a real generalization of the semantic framework that we have been stuck with from the very beginning. So until now, we have always had some sort of model in which propositions can be true or false. But we would have a fixed interpretation at one time, and we would be simply looking at logical combinations, perhaps driven by truth tables, in that one single world in which we were looking. With modal logic, we suddenly have a set of worlds. In these different worlds, different things can be true. So you have one world where Joe Biden is president, another where Donald Trump is president, and yet another where Kim Kardashian is president. And one could imagine links from one world to another. I think the easiest thing is to think of time. Time is by no means the only route from one possible world to another, but it's perhaps the most intuitive. So you could imagine that perhaps one president will serve out his term and then a different one will take office and so on. And then one might want to reason about which things might depend on which other things, not only within a single world, but as we progress from one world to the next. So modal logic allows us to talk about such things. To set up the semantics mathematically, we need a few things as shown on this slide. So we need to somehow specify a set of worlds. In terms of applications, for example, if you have a more practical application in mind than the presidency of the United States, you might concern yourself with possible machine states of a piece of hardware, and in this case the accessibility would be how one state could be reached from another state. Or as I have said already, one could think of the flow of time and looking at different time intervals as representing different worlds. Now, we're not interested in worlds in isolation, but in the possibility of moving from one to another. This is called the accessibility relation. That is part of our setup. So if we fix a set W of worlds and a relation R of being able to reach one world from another world, we now have a thing called a modal frame, or sometimes a Kripke frame, named after the guy who invented it. And with all this, we are able to introduce two new logical connectives, box and diamond. Box also means necessary or necessarily. Diamond means possibly. So if I write box A, that means A is necessarily true. Think of it as something like 2 plus 2 equals 4. And what that means in our semantics will be, if you consider the world we are sitting in now, and now look at all the worlds accessible from our world, if A is true in every one of those worlds, then we say box A is true. So A is necessarily true means that in any world that we can reach in one step from the current world, A will be true. Dually, diamond A, or possibly true, means that sitting in our current world, there is at least one world accessible from where we are in which A is true. So these are strict duals. So in particular, if it is not possible for A to be true, then it is necessary that A is false. Here's a little picture, which I would love to be able to doodle in front of you, but alas, I have to try and prepare it beforehand. So here is a general situation you might imagine. Ignore the bottom one for the moment. Here we have 4 possible worlds, and they are connected in various ways. So you see we have a world here in which P is true. And if I don't say that something is true, then you can assume that it's false. So if we have only P, Q, and R as things we're interested in, then here P is true, Q and R are false. We can reach this other world. I didn't bother to name them, but you could imagine that's W0, that's W1, or whatever you want to call them. This is a world in which P is true, Q is also true, and so on. So we have these various worlds. You see that here I have a link from that world to this one, then down there to another one. Those 2 worlds, there are links going in both directions. And finally, over here we have a world that has a link right back to itself. Now, looking at this top world in which we have P and Q both being true, here I'm saying that diamond Q is true. The reason, remember, diamond Q, possibly Q, means there is a link from this world to a world in which Q is true. And it is this link right here. So this world where we have QR is accessible from the world that we are interested in. I also claim that box R, necessarily R, is true in that world because every world accessible from here, R is true. The accessible worlds, well, there's this one, R is true there. The other accessible world is this one, R is also true there. Now, I invite you to work out for yourself for this other world where I say that diamond R is true as well as box P being true. Now, the first thing you might ask yourself is, do I really want to write these self loops? And in fact, we often will say we are only interested in accessibility relations that satisfy certain nice properties. For example, if you say that I'm going to assume that the accessibility relation is reflexive, that means implicitly there are self loops with all the worlds, and then if you're making a diagram, you don't need to show those self loops. Or, and now let's move to the diagram at the bottom, we're often interested in the passage of time, and we usually think of time as being transitive. So let's say if you will be earning a fat salary, dear, does that one work? Let's say if eventually you will be earning a fat salary, and then after that you'll be earning an even fatter salary. Well, that didn't work very well actually. But with time, you can see that if I can get to this thing, this P, let's call that the fat salary actually, in one step from here and then another step to there, well, this thing, if this is your fat salary, is still in your future from the original place in the beginning. So what I've kind of made a hash of is we could imagine this thing at the bottom being fleshed out with all the extra links that you would get from transitivity. That is, a link from there to there, a link from there to there, one from there to there, and so on, which would be an awful mess. So if we decide at the beginning that we are interested in transitivity, then we can say that somewhere. And then if we're drawing diagrams, we don't have to show all the additional links that are implied by transitivity. Now this diagram at the bottom is an example of what might be called discrete time. So it's time in the sense that we see this infinite progression going in one direction. Of course, you wouldn't have backwards and forwards links if we're talking about time, would we? It's discrete time in that we are envisaging separate clock ticks. Things get a little trickier if you say there is no such thing as discrete time and that every interval can be divided into smaller intervals. That's in fact not always so useful for us, though there are some rather ideological battles out there in the temporal logic world about exactly this point. In fact, we're not going to talk about a next time operator in this particular lecture. The other issue connected with time is the difference between what we have here, which might be called linear time, and branching time, where we say, okay, P can go to Q. Well, Q, this might be the Joe Biden election, but you might have the Donald Trump possibility here and the Kim Kardashian possibility there. So you could imagine branching off at any point and infinitely many different futures branching away from this beginning here, if you like, our Big Bang. You get certain properties are different depending on whether you have this linear time, if you like, a kind of predestination in which only one future is possible, or what is called branching time, where many different futures are possible. So we have, it's a very, very rich domain to talk about. Now, I'm afraid we need to do the formal business again. At least we are going to confine ourselves to propositional modal logic. It just keeps things a bit simpler for us to not have quantifiers and to not have those universes that make so much trouble. So we only have the and or not world. Now fix for the moment a modal frame, W and R. Now the notion of interpretation will be a little different from before. An interpretation will map our propositional letters to subsets of W. That is to say, for each propositional letter, I gives us the set of worlds in which that letter is true. I guess this is because we always imagine interpretations as giving a meaning to propositional letters. Now we have this relation here, which is pronounced to W forces A for reasons you don't want to know. But W forces A simply means that A is true in that particular world W. If the formula is just an atomic symbol P, then it's trivial. We look at the interpretation of P, and if our world W is included in the set of worlds where P holds, bingo, it is true. If we've got a propositional connective, then we use truth tables. So going way, way back to our Boolean logic, just use truth tables to recursively evaluate the forcing relation on A and B, and then combine the Boolean values. what about box and diamond? Well, these, and I did promise you would see a logical connective that was not definable by a truth table, and here it is. So box A is defined with the help of the accessibility relation, and W forces box A, if and only if, for every world V accessible from W, V forces A. This is the formal version of the explanation I already gave you. Equally, W forces possibly A, or diamond A, just if there is some V accessible from W that forces A. Now, continuing the usual semantic definitions, we will be finished with this soon enough. We fix a modal frame. Normally, a modal frame will set up our logical world for a particular logic we're interested in. And as before, the interpretation will be a more local mapping of the various predicate symbols to their meanings. So, having fixed these things, we say W forces A when A is true in the world W, as we have seen defined on the previous slide. But we could also bring W, R, and I into our notation to say that it holds for all little w in the set of worlds big W. We can also remove I to say that it holds for all I rather than any particular I. Finally, if we are really talking about all possible modal frames, then we can drop the W and R. They're no longer relevant because here we're talking about a formula A which is valid in every modal frame. So it is called universally valid. If you like, these are the modal equivalent of tautologies. And certainly all propositional tautologies will be universally valid. It turns out there are quite a few other formulas containing the modal connectives themselves which are also universally valid. But moreover, we are frequently interested in constraining our accessibility relation, for example, to make it transitive, or for much of this lecture, reflexive and transitive. And if we state that very clearly, then we might say universally valid with respect to those constraints, and we will get additional formulas to be valid in that sense. That was the semantics. Now, as usual, we need to move on to the proof theory. One way of doing this, well, you might remember from early in the course, we saw a Hilbert calculus for propositional logic. We can turn any Hilbert calculus for propositional logic into one for modal logic by adding an axiom. This, by the way, this K, and now I'm wondering whether K stands for Kripke or something else, so maybe one of you can find out and tell me. Anyway, K is the name of the minimal modal logic that merely has to satisfy this axiom here, called the distribution axiom, and this inference rule here, the so-called necessitation rule. This particular proof system doesn't say anything about diamond, so we have to regard diamond A as simply defined in terms of box, then expand them all out and do whatever proofs we have to do in terms of not box not, which, as usual with Hilbert systems, is a terrible pain. We should ask ourselves, why is this axiom and inference rule correct? So let's look at the axiom first of all. This is telling us that every instance of this formula for every for every formula A and B, which could be a modal formula as well, every instance of this will be assumed as an axiom. So let's convince ourselves, is it true according to our Kripke semantics? Well, let's assume we have the antecedent, that is, we have box applied to A arrow B. What does that mean? We know what A implies B means. Box A implies B means that in every world accessible from here, from the world we're looking at, if A is true, then B is also true. What does box A mean? It means that in every world accessible from here, and when I say here, we're always interested in truth in a particular world W. So in every world accessible from here, A is true. So in each of those worlds, A is true, but also A implies B. Therefore, B is true in every one of those worlds accessible from here, and therefore, box B is true. What about this necessitation rule? Why does that make sense? I suppose the way you think about it is this: if some formula A can be proved outright, then A is a theorem. And if something is a theorem, then it is true. It is a valid formula, so it will be true in all modal frames and under all interpretations. And therefore, it will not only be true in all worlds reachable from here, but indeed it will be true in all worlds, not just all reachable worlds, but all worlds. And therefore, box A. Okay, we have seen the modal logic called K, but as I mentioned, we frequently want to constrain the accessibility relation in various ways that might be regarded as natural. There are half a dozen to a dozen of these properties that people are interested in, and here I've listed the three that are the most common. So there's reflexivity, the idea that every world is reachable from itself, or to put it another way, we have the right to stay where we are and not move. There is transitivity, the idea that if I can get to a thing in 2 steps, it is still accessible. There's also the property of being symmetric, which we could express as saying, if I can get to some world W from here, then I can get back to here from W. So every link goes back the other way. So it turns out that if you assume reflexivity, you get a thing called logic T. If you assume, in addition to reflexivity, also transitivity, the resulting logic is called S4. If in addition you assume symmetry, and at this point your equivalence relation, I gave the game away. Your accessibility relation is reflexive, transitive, and symmetric, and therefore it is an equivalence relation. So at this point, your accessibility relation is partitioning the set of worlds into disjoint partitions, each of which is reachable from another, that is within a partition, but the various partitions themselves are absolutely unreachable from each other. There are many, many other properties of modal logics, but we will mostly be looking at S4 here. So that's reflexive and transitive. I ought to say a few words to justify why these axioms make sense. So axiom 4 says, if box A, then box A. Now let's ask ourselves why that makes sense. Well, let's suppose we're in this world here on the left. What does box A means? It means that in every world that's directly reachable from here, then from there, from every world accessible from there, A is true. In other words, sorry, what am I saying? If box A is true, put it round the other way, certainly A is true in every world accessible from here. But to be true for box A means that all worlds reachable in 2 steps, A is true. Now that actually works, I'm sorry I've mangled this a little bit, is because if A is reachable in 2 steps, then by transitivity it is actually reachable in 1 step. But if it's reachable in 1 step, thanks to the box A property, then it is true in that world. So A is definitely true in all worlds reachable in 2 steps, and therefore box A is true. It is also not too difficult to justify these other axioms. For example, if our accessibility relation is reflexive, and if box A is true in a particular world, since the relation is reflexive, box A being true in the world implies in particular that it is true in that exact world because the relation is reflexive. Therefore, the set of all the accessible worlds includes the very world we are talking about, and therefore A is simply true. This one about symmetry I will go through a little more quickly, and you just consider going to the other world and back again, and A will have to be true, because if you can go to another world, you can definitely go back to it again. So see if you can figure out symmetry. A much more difficult exercise for you is to prove the converse. That is to say, to prove, for example, that if we have every instance of box A implies A, then the accessibility relation must be reflexive. It's true, but it's not super easy to see. And similarly for the other two. So yes, if we have every possible instance of axiom 4 holding, then one can prove that the accessibility relation must be transitive, and so on. So now we are going to make the transition from modal logic to temporal logic simply by interpreting the accessibility of one world from another as the arrow of time. So now we can reinterpret the typical modal operators to have a temporal meaning in terms of the future and the present. Occasionally one will enrich temporal logic with the means to talk about the past as well, but it's not here. So now, box A. So A is true in every accessible world. For now, accessible will mean future, and in fact the present, because our accessibility relation, remember, is reflexive and transitive. So if box A is true, then A is true now, and A will be true forever into the future. What about diamond A? Well, this is the dual of box A, and it means there is some time in the future when A is true. Now, they get more interesting when you put certain combinations together. For example, box diamond. Well, that means from every point in the future, as far ahead into the future as you go, A will be true, so we can move up to the previous one. A will be true at some time in the future, after the future time I'm talking about. In other words, if you go forward a year, A will be true after that. Go forward 10 years, A will be true after that. Go forward a million years, A will be true after that, and so on. So A will be true infinitely often. So even at the time, one of the times when A is true, you can say A will be true again later. So dually, if we have diamond box A, this says that at some point in the future, A will, if you like, be latched to true. It will become permanently true. Now, I hope you can see that these are useful for talking about computer sciencey things. And for example, box applied to a safety property will say that your safety property will always hold. So if I want to express mutual exclusion as having the form not P and Q, then simply box of not P and Q will tell us that P and Q cannot be true in any future state. Or the next one, and it would be typical to have box in front of formulas we would want to prove by verification, because typically we would want some kind of good property to hold, everywhere, forever. So this says sort of everywhere or indefinitely into the future, if P, then eventually Q. So every occurrence of P will eventually trigger an occurrence of Q. Now I have my little teaser here. What about box A and diamond A? Well, in general, they can have various meanings, but in S4, thanks to transitivity, they collapse down. So for A, box A is what? It says forever into the future, from that point, box A will be true, which means forever into the future, A will be true, which is exactly the same as box A. Similarly, or dually, diamond A has the same meaning as simply diamond A in S4. Now, nobody likes to prove theorems in a Hilbert calculus, so it's time to use the Sequent calculus instead. I'm sorry to say that there are some tricky things going on here, and I find the temporal intuition is the best way to understand what's going on. You need to notice these things with the asterisks. You see that on the left side, whenever I have gamma with an asterisk, it means I'm throwing away a lot of stuff. Or to put it another way, I'm only keeping certain stuff very specifically. Gamma star consists of exactly the things in gamma that begin with a box. The delta stars are the duals. It consists of all the delta formulas it consists of all the diamond formulas contained in the original delta. So what is going on here? It means if I'm doing a backwards proof, let's say using this box on the right rule, and I'm trying to show some gamma arrow delta box A, and as you remember, gamma and delta merely represent lists of other formulas which we don't bother to write out or specify at the moment. But if I apply this box on the right or this gamma on the left, I have to apply this gamma star and delta star, which will have the effect of throwing away all the side formulas except on the left, the ones that begin with a box, or on the right, the ones beginning with a diamond. Why does that make sense? Well, I think, as I said, thinking about time is the most sensible way to do this. So if I am claiming here, if I'm trying to prove box A, remember what box A means. It means A will be true forever. So imagine that we have a time machine and we want to check that A will be true forever. How do we do that? Well, we climb into our time machine, we zoom into the future, into some random time in the future, and we want to check that A is true, that we can prove simply A. Now, in the future, we can't count on everything being true in the future that was true at the present. So probably Kim Kardashian is not the president of the United States anymore. And yet 2 plus 2 will continue to equal 4. And that's what these stars, these asterisks, are doing here. The idea is we zoom into the future. Most things that were true back where we started are no longer true, but the eternal truths, that is the things beginning with a box, they will be true forever, so we keep those. As for the diamond formulas on the right, remember they are simply dual to the box formulas on the left. So that's why that rule makes sense. Turning to the box on the left rule, it's a bit more straightforward. So you are in a particular time and you want to show some sequent, and you know that A is true for all times into the future. Now you say, okay, now is the time I want to use it. So you throw away the box and you say, let's go with now being the time when I'm going to need A. The rules for diamond are dual. Possibly our time machine argument will help us to make sense of diamond on the left. So I'm trying to prove a sequent, and I have the formula diamond A, which remember tells us eventually A will be true. So we use our time machine and we ask our time machine, this time we don't want to go to a random time. We ask it to take us to a time when A is true. So the time machine obligingly does this. But as before, we can't count on Kim Kardashian still being president of the United States, and we can only count on those formulas in gamma that are eternally true and dually for the ones in delta. And finally, for the delta on the right rule, if we are trying to show that A will eventually become true, one way that can happen is if A is true at this exact moment, so we simply throw away the delta. Now we need some proofs to demonstrate this. So what I'm going to do is use our sequent calculus to prove the distribution axiom. And if you're wondering what does it mean to prove an axiom, remember I am proving a formula of a different logical calculus. So I'm showing that our sequent calculus can justify this axiom for a different calculus. And what I have done, I've already done the implies reasoning for you. So we have a sequent in which we are assuming box A implies B and box A, and we want to show box B. Now, as you remember with the sequent calculus, you can only eliminate an outermost symbol, and you might wonder which one to eliminate. It can be very tricky here because if you go wrong, you will lose the possibility of proving your theorem. And if you kind of cheat and prove it anyway by applying the rules incorrectly, you will lose a lot of marks. But what we do here is we see I have got two formulas on the left with boxes in front of them. These are eternally true formulas, and I decide I will keep them. I will do box on the right instead. And because these formulas on the left side are eternally true, that is, they begin with a box, they are kept when we apply box on the right. And now it will be trivial. We can apply box on the left, which doesn't have any weird preconditions. And then we immediately get something which follows from basic sequent rules. Here's one that is a little trickier. What do I mean by an operator string equivalence? Well, I am trying to show part of this, as you can see here, this weird combination box, diamond turns out to be equivalent to simply box, diamond. That is in S4, not generally in modal logic. We have, in fact, also box is equivalent to box, which means that in S4 modal logic, we have only these. One has to say 7 different modalities, because we have these 6 combinations here, plus the empty modality, and these are the only distinct ways of prefixing a propositional formula in S4. Trying to remember what this one does. Well, figure it out for yourself. So we're trying to prove this. What do? We say, well, I have this thing which is eternally true. I have to prove a thing that's eternally true, so I'd better drop this box on the right. So I do that. Now, and we maybe need the ability to look ahead a little bit. You might want to see that if you were now to drop this diamond on the right, that you would get into trouble. Remember, a diamond on the right formula is also eternal. So we can drop this box on the left instead. This has no preconditions, or crazy side conditions, I should say. Now where are we? I have diamond on the left and right. The diamond rule on the left will throw away stuff, but it will keep my diamond on the right formula. Now we have box diamond, and it's now easy because I can just throw away the box. This has no side conditions, and we are finished. Now, it's useful to see when proofs fail. So here are 2 examples. This first one, and you wouldn't want this to be true, so this sequent at the bottom here is saying that if A is true, then A will be true infinitely often. That is to say, box, diamond, A. We can't prove it because when we apply box on the right, this formula A here on the left is just A. It's not eternal, and therefore it must be thrown away. And so we are found unable to prove this A, and so that proof will fail. Compare it with something that does make sense. So clearly on the left here it says A is true forever, and this says A is true infinitely often. So obviously that does make sense. And when we do very similar steps, you see when we apply box on the right here, the left-hand side is preserved because it is eternal. Now we can throw away the diamond. Now the next steps are to throw away the box, and finally it will be a basic sequent. So this one on the right side here that has the assumption of box A will become a valid proof. Down here we have another example of an invalid proof. And looking at the formula, we should try and convince ourselves that that it doesn't look very likely. So if at some point in the future I shall be an archbishop, and if at some point in the future I shall be a ballerina, does that imply that at some point in the future I shall be both an archbishop and ballerina? Well, and intuitively we say, well, they will both happen, but they don't have to happen at the same instant. And this is what will happen. So if you like, when we apply our diamond on the left rule, we are hopping into our time machine and saying, take me to the time when I am a ballerina, presumably a younger age from being an archbishop. And there you are, you are a ballerina, but now you try and prove this formula and you take away the diamond. You can show the ballerina part, but you cannot show the archbishop part. Now, a nice thing is where all this can go if we develop it further. So we can make a full transition from modal logic to temporal logic. So we can define, in fact, a richer language with more temporal operators, kind of, where, for example, formula P holds true until Q becomes true, and many things of that sort which are useful for expressing a richer range of temporal properties. And you can use tools called model checkers to automatically, I was about to say prove, but they're not really proved. So they are rather checked. So you take your modal formula, or I should say now your temporal formula, and you are able to make typically a finite set of models, maybe through cheating. In other words, maybe it should be an infinite set and you are using some not necessarily sound state reduction technique to reduce it to a finite set, or maybe in fact one can show that a finite model is sufficient for the formula you're looking at. Then using very clever techniques, the various states, which could be in the millions with modern methods, can all be examined to check that the temporal formula holds in every one of those. And it is a tremendously powerful verification technique. It's not in this course for a couple of reasons. One, that it is not based on deduction, so we're not doing theorem proving in the usual sense at all. But also, it is very much a big subject in its own right. The various issues that I mentioned apply here. In particular, and annoyingly, the difference between branching time, or the choice between branching time futures and linear time futures, is frequently made on the basis of how efficient the model checker can run, rather than, as it should be, on the assumption that is the most reasonable for your application area. And equally, there are contexts in which people want to have a next time operator, i.e. they want to say, if P holds now, then Q will hold at the next clock tick. And there are other people who will insist that discrete time does not make sense in the world of computers and want a language in which time is continuous. There are many, many computer sciencey systems where this sort of reasoning is relevant. So in particular, anything involving concurrency, because typically one is interested in properties such as mutual exclusion, and also one is interested in the long-term behavior of your system. Hardware systems are, of course, concurrent systems. There are many, many model checkers, and an interesting thing is that this one called new SMV is based on BDDs as an internal data structure. and there is this thing called spin and countless others.